I'm also from Vienna, and the last 1.5 years I've spent writing a book with my colleague from Berlin, Konrad Koltier. We wrote the book in German with the strong hope that it will be translated pretty soon into English. The book is called Images of Mathematics, and it was only 5 days. 5 days to the figure, but I don't have any copy. I asked the publisher, Springer Verlag and Sektum Akademische Verlag, to provide me with copies, but they didn't make it to that time, so it will be on the market soon. And but before I want to say something, because you maybe have mentioned, noticed that I've taken pictures of almost everyone here, and I'm also a professional photographer. And if nobody objects, or if people don't object, then I put the images on the website, the name of which I will give you at the end of the talk. If someone has objections, just come to me and I don't put it on the website, okay? So, let's continue with the images of mathematics. Maybe I would show you the PDF just briefly. It looks like this. And it's really full of images. And I wrote 1001, and it's probably true, it's probably more. And we were not alone. We were assisted by 3 of my assistants, and in Berlin also 2 more people to get that work done. One of the major things was, besides making the pictures, was to write text that is so short and describes the major thing, and then to find out the literature which can be obtained in the internet, or books or articles that have been written about, for example, the supercyclic. Almost no one would know what it is, and then you have different links in the internet and whatever that explains you where you can find more information. So this is the PDF, and I go through the single pictures here. Of course, not too all, because I wouldn't have the time. We have 15 sections, and one of them is polyhedral models. I removed pages that now would perfectly fit into the context, because I saw many things that are also in the book. Here's just one example of the tetrahedron, this so simple thing, but with so many extraordinary properties. And one of them was discovered or checked by Weiss and Havlicek in Vienna, that the heights of the tetrahedron lie on a hyperboloid, which then can be calculated and then geometry in the plane.
That's arbitrary tetrahedron.
Arbitrary tetrahedron. And special hyperboloid. It goes to whole mathematics. I'm a mathematician, but still, of course, I cannot know everything in mathematics. Not even a third or whatever. But we picked out different things, different topics, and tried to take pictures of it, make pictures of it. For example, we didn't find any picture to the following problem. Given a closed line, can you always find a quadrangle, a square with the 4 vertices on the line? And it's not trivial at all, and it has been proven in the past. It's possible, but there are one or more, but not infinite. Whereas if you take curves, arbitrary closed curves, and try to put regular triangles in it, there is always an infinite number, which was amazing for me as well. All the new problems, the transaction of the angle is a very old problem, as you know, and this is a new one. We have three objects of whatever kind, and we try to make one intersection so that all the three objects are, by volume, divided into two equal parts. It's called the ham and ham sandwich theorem. Then about formulas. For example, the binomial coefficients, so the Pascal triangle, and then make some pictures out of it, and then take even the trinomial coefficients and make pyramids out of it. Or functions and limits. The Weierstrass function, for example, and its derivation. And as I said, the problem is you have half a page and write such that people get into the topic a little bit, understand what the problem is, and if they're interested, get more information. Also, one non-trivial thing, if you take a cup of coffee and stir it up, there will be always one molecule on the same point as it was earlier. The fixed point theory. And then about curves and knots. For example, the spherical conics that can be kinematically created very similarly to the planar conics. Or we saw that image in another context today, Apollonian circles as orbit of points where the product of the distances of two fixed points is constant. Sorry, the ratio is, and here, if you want the product constant, then you get the Cassini curves, which appear in space, for example, as the planar intersections of a torus. Geodetic lines, not only on curved surfaces, but also on polyhedra. And the explanation how it works, how you would calculate that. Knots. And the thing was not only to produce beautiful pictures. The thing was always to get some provide some additional information. Not only a picture book, make always a picture book, but also a mathematical book. For example, the Celtic knots, I explained thoroughly how they can be knotted. Then, of course, much about the geometry and topology of surfaces. Start with simple things like the coordinates. The prototypes of all surfaces, you know. And then a surface of degree 3, for example, the famous Krebs surface, which carries exactly 27 straight lines, which always run through certain points, the Eckhart points, and so forth. I have to say something that not all pictures are created by us, by Mama Cortina and me and my sister, but also many pictures stem from other mathematicians. Okay. This is, for example, Hans-Peter Schroeter. The pentaconoid, how it can be created by motion, or say you take a knife and cut into a petal and then try to unfold that, and what happens and how can it look like. And then applications, this is for example Helmut Gottman, applications in modern architecture with pure geometry. Then classical things like the Mobius strip in different variations, and also topological examples, the kind of. And then some other topologically interesting surfaces like a cycle surface. And Alexander's sphere. Then Portier is a specialist for minimal surfaces, so most of these following examples stem from him. The Jargon problem and classical minimal surface, because the surface we had already today. And then also discrete minimal surfaces. This is a modern trend in mathematics that everything is discretized, or that's the correct word. And the examples we had earlier are also kind of examples of this. It's not perfect, but somehow it works. A minimal surface, how can you discretize a minimal surface? In principle, you would have to can zoom it in any way, and always have to be minimal. But generally speaking, you can discretize it or put circles on surfaces. Then there's done a lot about packings, and explained how we have different kinds of pavements, for example, paving. Monuments. And the 17 symmetry groups systematically shown. Goes to the non-periodic pavements, then the Voronoi thing, and also just 5 sentences explain what is a Voronoi diagram, and it takes a while to get it there. But then you have been forced to do it, and what was quite interesting for me, for me personally, that it was really a development for myself. 5 sentences explain what a Voronoi thing is, so that everyone can repeat it and understand it to a certain extent, of course. And then again, beautiful examples, and extend it to 3D space. And we developed so many programs in the meantime which can do those things. Most of the pictures were done in open geometry, which is the system that we developed much earlier, which has developed with that kind of work we did now. And this is dimensions, higher dimensions now, the hyperbolic space. We have that today as well. Or for example, by Helmut Starker in Vienna, the investigation whether Escher had known all those things or not. And Starker came to the conclusion he knew everything about it, although he cheated a little bit, but he must have known many things about it. And then 4-dimensional polyhedra, like the 120 cell dodecahedron. Of course, we can only show 2-dimensional pictures, not even 3-dimensional, 2-dimensional pictures, it's always the same. But it looks somehow, obviously, to be, no one can tell me that we would now know how such a thing looks like in fourth space. But anyway, it's a projection.
Your classes.
And then classification. This, for example, was done by Fritz Obermeier. Nice images from inside 600 cells and so forth. Then about graphs and incidences. Simple example, touching circles. And if you do the three-dimensional interpretation, then you get quite interesting things. For example, this, if you consider the hull of all those circles which define spheres, then the hull of the sphere is a pancyclic. And then we come to the movable forms or geometries. You know probably that the elliptic motion is defined by a rod of constant length, which is guided along two straight lines. But if you extend that to 3D, again, two straight lines and a rod of constant length, and you move it around, it's also in a kind of elliptic motion. And for example, each point on the rod has an ellipse in a parallel plane as partner, as orbit. Then those things that are terminated, the kaleidoscopes, which can be interpreted in different ways. For example, if you take that part of a, it's actually a part of a cube, a cut-out cube, and then you, then you can move that whole thing and create new spaces, which is interesting, for example, for modern architecture, to create new spaces by motion. This is from Otto Russell. Something that was not supposed to move, if you count the degrees of freedom, but it's easily to be moved, it can be moved in two different directions, completely freely. And then some simple things like the low triangle, which can be turned around in a parallel strip. And then you might ask if a low sphere could also be moved within kind of prism. Cannot. This image was by Fritz Mannhardt. Then something interesting, two Hungarians discovered that Gömbötz. Gömbötz is a strange thing that if you roll it somewhere, it will stand up in a certain position, always. But not due to lead inside or something, due to the geometrical shape. Fractals, we've seen that picture today, similarly, and the inverse curve, extended to three space-filling curve. And the curves I had already today. And then we had, for example, the task to put such a thing on a sphere, which is not trivial at all. And we got also help from Dr. Weiss in this case. And it describes how it is done. And then the fractal dimension. What is a fractal dimension? How, for example, the Koch curve goes to a space-filling piano curve. And all the pictures, of course, done in a resolution 3000 times 5000 or something, which was also a challenge. And then the Menger sponge we had already today, for example, has the dimension 20 over 27, because you always put 27 out of the cube in each step. And the pictures stem from Gerd Beer. Then we always see the Mandelbrot-Menge set, but here is the explanation why that works. And of course we have the Julian-Menge and all the stuff. I just took some sample pages. And the curly Q fractals And then random walks, which was an interesting topic also. For example, if you randomly walk around in a plane, then you have a borderline, and the borderline is a fractal of dimension 4/3. And then do that with some restrictions in free space, and you get quite interesting things like this. So all random walks, but with certain restrictions. Percolation. Let's take a picture on the next slide. Here you can see how from above to down could a liquid go through or not. How many percent of the mini cubes of the voxels have to be filled? It turns out it's 59%. If you fill 59% randomly, then you have guaranteed that the water or whatever can percolate. And it's always the question, do we have pictures of that, you know? Sometimes you find things in the internet, many times you find things in the internet or in books, but many of the pictures are completely new, hopefully. Then mappings, and my special field right now, because I do photography all the time, the collineation, when you put something in front of the lens, and you get not a two-dimensional image in behind, but you get a three-dimensional collinear distracted object behind the lens. And then you take a chip, the sensor, and have to make a crossing section. And it is painted, it's not the same if you take pictures of big things or small things. So it's completely different. Like the speaker before said, it's not the same small or big. Also in photography, exactly the same. The problem, the smaller, the less depth you get. Then some things with complex numbers, polynomials, and we also took Bachmann's example of the heart. He needs heart. And this is also zero manifolds of polynomials done by Jorg. And then finally some applications of mathematics, like the currents and turbulences. And then electric field lines, which are solutions of differential equations, of course. And then I put it in again, and I put it out that we have a drum today, which you could not hear. So this drum is impossible to hear, and it's the outlet. And one of the last examples, how to find, it's a traveling salesman problem, how to find the shortest way in between n points. And it turns out that even the fastest computer could not solve the problem if you take 100 points. So if you can manage with 100, then you take 1,000 points, you could calculate for the rest of the universe. But the ants have found a way. If someone is interested, I can explain later on. And then I just wanted to give you the link to the home page if you want to know, to write it down. So from there you can download the things, the pictures I did. Don't write www, just Savannah would be enough. And thank you for listening.
We're only a half an hour behind, so we won't take questions
which you all know what he looks like. Now, Georg, I must have this book. How do I get it? You got a copy with you?
Yeah, I just said earlier that I missed it for 5 days. In 5 days it will appear. So my next talk will be in Germany, and then I will provide people with the copy. But right now I don't have it with me. So how can I do it?
Yeah.
Made it.
I must have this book.